Pressure energy. Pressure energy. To derive a relation for pressure energy, let us imagine a cylindrical container. A cylindrical container. In this cylindrical container or vessel, suppose a liquid is taken, and this cylindrical vessel carries a side tube with an area of cross section A. With an area of cross section A. If the pressure on the liquid near the cross section of the tube is say P, near the cross section of the tube is say P, due to the liquid, then by applying the same pressure, the liquid can be pushed inside. Let us suppose this small tube is fitted with a piston. Then the pressure on the piston is P. By applying an equal pressure P, if the piston is pushed inside by a small distance dx, then the force applied is Pa. Where P is pressure applied, A is area of cross section. Since dx is the distance moved, then the work done is equal to Pa dx. This work done will be stored in a small volume of the liquid, which is equal to AdX, and we call this as the pressure energy of this liquid. Applying a pressure P, if the piston is moved inside by a distance dx, we know that the area of cross section of this side tube is A. Hence, the volume of the liquid pushed inside is AdX. And its mass is AdX rho, where rho is density of the liquid. Volume is AdX and mass is AdX rho. Sometimes we understand the pressure energy with pressure or pressure by density. We can derive this relation like this. Pressure energy per unit volume is energy by the volume of the liquid. Then pressure energy is equal to Pa dx, and volume of the liquid pushed inside is AdX. So Pa dx by AdX gives pressure energy. It is equal to P. So we can understand pressure P as the pressure energy per unit volume. Pressure energy is Pa dx, and mass of the liquid pushed inside is AdX rho. Hence, pressure energy by mass is Pa dx by AdX rho, which is equal to P by rho. Hence, P by rho is understood as the pressure energy per unit mass. So, pressure energy is equal to Pa dx. Pressure energy per unit volume is P. Pressure energy per unit mass is P by rho. Certain characteristics of the liquids or fluids. A liquid should be incompressible and non-viscous. So, a liquid will have a property of viscosity, viscous or non-viscous, or compressible or non-compressible. Here we consider a liquid which is non-viscous and non-compressible. When it is flowing, the flow may be steady flow or non-steady flow. We consider a steady flow for the study of the fluids. Then there will be rotation in the flow. So we consider non-rotational flow. So we consider rotational or non-rotational states of the fluid, and we take non-rotational, steady flow, incompressible liquid, and non-viscous liquid flowing steadily without rotation. These are the properties which we take while studying viscosity. The characteristics of the fluid are incompressible, non-viscous, steady flow, and irrotational flow. When a liquid is flowing in a horizontal pipe of diameter d, its as its velocity increases at one particular state of velocity, the steady state will turn into a turbulent flow. A steady state of the liquid will turn into turbulent flow. Mathematically, it is described with a velocity known as critical velocity. Mathematically, it is described with a velocity, critical velocity, and it is calculated with an empirical formula. Vc is equal to R into eta divided by d rho. Vc is equal to R into eta divided by d rho, where Vc represents the critical velocity, R represents a constant number known as Reynolds number, d is diameter of the tube, and rho is density of the liquid, eta is the coefficient of viscosity, which we are going to study now. Reynolds number R. With the value of R, we mathematically study the state of flow. When R value is less than 1000, for a value of R less than 1000, the state of the liquid is considered as steady state flow or laminar flow or steady flow. If the value of R is greater than 1500, then the state of the flow is known as turbulent flow. If the value of R lies between 1000 and 1500, then it is the state in which the state is turned from steady state to turbulent state, the transition state from steady to turbulent. Like this, we express mathematically the state of flow of the liquid. Streamline flow or steady flow. To understand this, let us consider a flowing fluid. Let us represent the path of the particles flowing in the fluid by the curves shown in the figure. The three curves indicate the paths followed by the particles of the fluid, and we notice that the particles will be a set of particles, a number of particles will be crossing along each line. While flowing along these curved paths, if all the particles have the same velocity at the same point, at a particular point, if all the particles have the same velocity, then we say the fluid is in steady state. The fluid is flowing in steady state or in laminar flow. Same velocity means same magnitude and same direction. The magnitude of the velocity should be the same and direction should be the same. This velocity will be constant at a particular point. At different points, this constant velocity will have different values. The line along which the particle is traveling is called streamline. While flowing in steady state, the energy of the particle is utilized. In overcoming the frictional drag. Properties of streamlines. They are smooth curves. Streamlines are smooth curves. The tangent to the curved path is the direction of velocity of the fluid. These lines, they do not intersect with one another. The streamlines do not intersect with one another. They are crowded when they pass through a narrow cross section, and they spread out when they pass through a wider cross section. In the figure, the left part is wider than the right part. In the left part, the streamlines are spread apart. In the right part, the streamlines are crowded together. So, when they flow from larger cross section area into a smaller cross section area, they get crowded. So, in a larger cross section area, they spread out. In a smaller cross section area, they narrow down and they pass closer to one another. Tube of flow. It is an imaginary tube. Let us take the streamlines and let us consider cross section, a circular cross section perpendicular to the streamline flow, the flow of the fluid. Consider the streamlines tangential to this cross section. These streamlines, they can be imagined to be flowing along the surface of a tube. They can be imagined to be flowing through the surface of a tube. Such an imaginary tube is called tube of flow. When a fluid is flowing in a steady state, the mass of the fluid entering one cross section is equal to the mass of the fluid leaving from the other cross section. If the cross section is different, the fluid enters a smaller cross section and it leaves a larger cross section, then the mass of the fluid entering the smaller cross section is equal to the mass of the fluid leaving the bigger cross section. In unit time, the mass entering is equal to the mass leaving. Like this, the fluid flows in a steady state. Equation of continuity. When a fluid is flowing in a steady state, the mass flow rate in a tube of flow is constant. Consider a tube of flow with area of cross section A1 on one side and A2 on another side. If the density of the fluid entering is ρ1 and the fluid is entering with a velocity v1 at the cross section A1, if the fluid is entering the tube of flow at the cross section A1 with a velocity v1 and ρ1 is the density at this cross section, and it is leaving the cross section A2 with a velocity v2 and the density of the fluid is ρ2, then the mass of the fluid entering the tube of flow is A1 v1 ρ1 per second. A1 v1 is the volume entering per second. A1 v1 ρ1 is the mass of the fluid entering the tube of flow per second. A2 v2 is the volume of the liquid leaving per second. Then A2 v2 ρ2 is the mass of the liquid leaving per second. So the mass flow rate is A1 v1 ρ1 and A2 v2 ρ2. Since the mass flow rate is constant, A1 v1 ρ1 is equal to A2 v2 ρ2. A1 v1 ρ1 is equal to A2 v2 ρ2. We know that the mass flow rate is constant and it is given by the relation A1 v1 ρ1 is equal to A2 v2 ρ2. If the liquid is incompressible, if it cannot be compressed, then the density is constant throughout. For an incompressible fluid, the density is constant. So the relation becomes A1 v1 ρ is equal to A2 v2 ρ. Hence ρ gets cancelled and we get the relation A1 v1 is equal to A2 v2. A1 v1 is the volume of the fluid entering per second. A2 v2 is the volume of the liquid leaving per second. So we can call it as flux, volume flux. So the flux rate is constant. The volume of the liquid entering per second is equal to the volume of the liquid leaving the tube of flow per second if the density is constant. That is for an incompressible fluid. We can explain some natural phenomena with the flux flow is constant, flux rate is constant. A1 v1 is equal to A2 v2. It represents the flux rate is constant, or volume into area of cross section VA is constant. From this we will get V is proportional to 1 by A, or A is proportional to 1 by V. V is proportional to 1 by A can be used to explain the water flowing from a hose pipe. While gardening, if you narrow down the mouth of the hose pipe, the speed of water increases. From the relation V is proportional to 1 by A, as A decreases, V increases. V increases as A decreases. When we narrow down the pipe, its area of cross section A decreases, hence the speed of water increases. We notice that the water coming from a tap, when it is falling, its area of cross section will be decreasing. The area of cross section of the water falling through a pipe decreases as it comes down. As it comes down, the velocity of water increases. The velocity of water increases, hence the area of cross section decreases. So A is proportional to 1 by V. When V increases, A decreases. So area of cross section decreases as the speed of water increases when it comes through a pipe.